This is session 6, extension and retraction systems for the Airbus A350. We are now on to the landing gear part of extension and retraction. There are two control and indication systems. They're exactly the same. They are redundant sides. You have LGCIS 1 and LGCIS 2. And each of the sides has two CPIOMs, that's your core processing input-output modules, also a common remote data concentrator, and your solid-state power controllers. When is it in control? When is this landing as the extension and retraction system in control? It's going to be in control when the selector lever is in an up position and the active side becomes inoperable. So they have the two sides, and they're not operating at the same time. You're going to have just one side controlling the system at any given time. And that's going to be monitored as well. Besides it being controlling the system, there's going to be a continuous monitoring through the Autoflight Data Exchange Network. Okay, so if you have one side that's not going to work, then the other side is going to become active. All right, and the supply, as far as electrical, just so you know where the supply is for the CRDCs and your SSPCs, is coming from 28 volt DC. All right, now what about the different valves that are involved with the landing gear extension retraction system? We are involving different valves. There's going to be your isolation valve, that's just isolating the hydraulic circuit from the normal supply, and here we're talking about the extension retraction, and then gear up lock and door up lock, and your gear selector as well as your door selector valves. The hydraulic supply that it's coming from for the operation of the extension and retraction is from the yellow hydraulic system, and the yellow hydraulic system operating the nose landing gear, and then you have the green hydraulic system operating the main landing gear. Okay, now the valves are being controlled by the CPIOMs, the ones that I just mentioned to you, and it's going to be giving those signals necessary for the valves to move accordingly. Okay, so moving in the commanded position. And then those valves are going to be sending the hydraulic supply, obviously, to their actuators in the right timing. Okay, so that's what they're doing. All right, let's go ahead and we're going to look at also just a real quick thing on the landing gear control lever. There's the balk device there to protect from the lever not being, staying in the position it needs to be. Time for a little review question. When is the LGCIS in control? Is it when it is in the up position or when it is in the down position? Okay, the answer is the first one, right? When it's in the up position. Let's go ahead now into manifolds. Okay, what manifolds do we have? Well, there are two manifolds that are used. We have one that's going to be controlling the nose landing gear, and the other one's going to be controlling the main landing gear, and then just controlling all the equipment related to each of those. Okay, and then just know the main landing gear is using the green hydraulic supply. Your nose landing gear is using the yellow. Okay, the manifold assemblies are actually integrated with their valves, and they're used to control the normal system of operating the landing gears. You also have some door sequence valves that send the hydraulic fluid to the open or the closed side of the door actuators. The gear sequence valves are going to send that fluid in order to either extend or retract, right? That's what it's there for. So remember, two manifolds, one for main landing gear, one for nose landing gear, and then you have the isolation valves. We're going to talk about a little bit. The up lock units. Okay, so we have isolation valves. Now, the isolation valves are there for what purpose? Okay, they're going to make sure that there's pressurized hydraulic fluid, right, for the normal operation of the extension and retraction of the gear. All right, and then you have the LGCIS module that's going to make sure that that valve cannot be energized when the aircraft is in flight and on the ground during the takeoff and landing. And that's what isolation valves are for. Just a thing on the landing gears and doors, they have the up-lock units, and they're just locking the landing gears and the doors in the retracted and the closed position. All right, so, and that's, you know, whether what the pilot's commanding, whether it wants up or down, retracted or extended, right? That's the pilot input from the landing gear lever. All right, let's go to a test question, potentially. What is the function of the isolation valves? Is it to ensure pressurized hydraulic fluid is available to the flight controls in LGERS, okay, your landing gear extension retraction system, or to B, to ensure pressurized hydraulic fluid is available to the normal operation of your LGERS, your laggers? It's B, right? Okay, and to ensure pressurized hydraulic fluid is available. All right, now let's go ahead and go into the monitoring of all of this. And the monitoring is obviously you have to have sensors when we're going to be monitoring. So you know, what exactly are we monitoring? But let's look at the components we have. There are proximity sensors that are positioned at the gears and the doors, and they're there to transmit data, okay, back to the LGCISs. You have the different monitoring of things that's going to be for your main landing gear and your nose landing gear doors, up lock and down lock. You're also going to have monitoring of the bogey. Okay, it's going to be your dip position on the bogey, and then nose landing gear shock absorber that's going to be extended and centered. It's going to monitor that. Also your main landing gear and nose landing gear doors fully opened, and also the shock absorber for the main landing gear. So both shock absorbers, main landing gear, nose landing gear, and then your main landing gear and nose landing gear doors fully opened. There's sensors at each of the locations, one for the landing gear control indication system, side one, and then one for the other side, right? So one for each. There's also, so you have proximity sensors, and then there's proximity sensor adjustments that would need to be made. So let's just go a little bit in that, and then I'll come back to talking about the sensors for the bogey beam. On the proximity sensor adjustments, remember I said there's one on each side, one at each of the LGCIS, and then you have adjustments that are needing to be made. And what adjustments? Okay, what are we talking about here? Well, you're in maintenance, so you know the sensors can be adjusted when they need to, when it's the task that you need to do. You can do that with the bolts and the nuts on the target or on the sensor. And there's a way to do all this with an existing gap between the sensor and the target. You can also use the shims, calipers, or you know anything else that they may specify for you to measure the gap. Okay, and you can again use the shims to get the necessary gap. So you're just you're making those proximity sensor adjustments to have that measured gap. Okay. All right, so let's go back to the monitoring. I talked about the sensors at each location, and then you also have the bogey beam position, so you need data on that, and then there are 4 sensors related to that. So 4 sensors are going to be sensing the position of the bogey beam, and they're going to be sending the data to the LGCISs. And they're going to be measuring the movement between the target on the bogey beam and the sensor on the sliding tube. So those are the 2 components. Remember I talked about the bogey beam assembly. The bogey assembly, there's the bogey beam, and then you have the sliding tube. Okay, that's that sliding tube, which is your inner piston to the shock absorber. Okay, and then you got 2 sensors for each channel. Each sensor monitors the movement in one direction. All right, so that gives you an idea with the monitoring using these sensors strategically placed. Okay, all right, let's talk a little bit on the weight on wheel on, we're talking about the weight on wheels. This is another, it's like another sensing that's going on with the extension and retraction system. What it's going to be doing is sending data, okay, weight on wheels data, to the other systems on board the aircraft to show that the aircraft is either on the ground or in flight. And it's going to be calculating if the weight, is on wheels for each gear, if it's balanced, essentially. But there's a logic that's going on. This is all done by the Common Remote Data Concentrator that's doing an AND logic of the output from those two sensors. Okay, it's going to show that the gear is downlocked, or that the shock, the shock strut is not fully extended. So then what happens when you don't have a full extension? Okay, it's saying, okay, you've got AND logic on the output from two of the sensors that are showing one downlocked and then one showing that the shock strut is not fully extended. And when that is the case, then there's going to be a gear on ground signal for each of the Common Remote Data Concentrators. Okay, all that data from the Common Remote Data Concentrators are going to the LGCISs 1 and 2. Okay, all right, so that's the weight on wheels data. You also have an alternate, because what happens, you have normal operation of your extension and retraction, but let's say something gets hung up for different reasons, and it needs to, there needs to be an input from the pilot to go to an alternate operation. There is a module in the cockpit. It's an alternate extension control module that would need to be pushed or moved downward in the downward position. That's third position is the down position, so that's the down command, and that starts the triggering of the alternate extension system. Now, what is involved with this alternate extension system? Their alternate extension is just that it could be maybe there's not a hydraulic supply getting through or something like that. You have alternate power packs that are part of the alternate extension system. So 2 alternate power packs, those are converting electrical input power to hydraulic output power. And then what other components do we have with the alternate extension system? Well, we have vent valve, because we don't want to have a hydraulic lock in that scenario. So there's vent valves, and then the door and gear up lock release. Okay, that's part of it. All right, so that gives you an idea with the alternate extension concept, just that it being there, and if you have a failure on the normal side, then that input of down in the down position on the panel in the cockpit will actually start the alternate extension system, and that's going to release those door locks so that you have the extension gear obviously coming down. Okay. And just like all systems that are backups, they're not going to be tied to the main ones, and that's the same thing here with the alternate extension system. It's independent of any other systems, your out-of-flight data exchange network, for example. So it can stay intact with doing what it needs to do. All right, and just for remember I mentioned about the alternate extension control modules, there are 2. There's going to be one for the main landing gear and one for the nose landing gear, and they are labeled A and B. Okay, so just so you know, there are 2 of those. Okay, so now you know about the power packs. There's one for the nose landing gear, and then one for your main landing gear, and it's isolating the hydraulic circuit right from the normal hydraulic supply. And then you have vent valves, and you have also have fill bleed valves that are installed on the vent valves. Okay, so that gives you an idea with the components that are involved with the alternate extension just be aware there are a few other components like indicators and whatnot of positions, you know, so you may see that. Well, that gives you an idea with that. And if you have any questions about extension and retraction systems, please do not hesitate to email us, and we'd be happy to answer to the best of our ability. Welcome to session 7 on the nose wheel steering system. This is part of the GenFam for the Airbus A350. Before I get into talking about the nose wheel steering system, I want to just mention the aircraft towing and pushback precaution, because you can cause damage to the retraction of the nose landing gear. And what I'm referring to in particular is the centering. Typically when we have nose landing gear, the shock absorber has cams that are used to center the nose wheels during the sequences for extension and retraction. And when the shock absorber extends, then that's when the cam on the sliding tube, which is the inner piston, is engaging into the cam on the main fitting. And that way it just causes that alignment. You don't want to have that alignment on the ground. It says, but what happens is you want to have, there's a measuring or a reference point with the H dimension, and if it's more than 385 millimeters, roughly about 15.6 inches, if it's greater than that, then you're liable to cause damage, so to the retraction part. So that's just a precaution when you're doing any kind of towing with the aircraft or pushback. Okay, just know that you could have a problem with the damage. All right, let's go ahead and proceed with the topic of nose wheel steering. And there's quite a bit of material in this particular session, but we'll get this bit at a time. All right, we're talking about the steering of the nose landing gear. There's different inputs you can have. The first type, or actually the first is going to be more primary, is going to be your inputs from the steering hand wheels. There are 2 of those. You have those, but you can also control it by autopilot and the rudder pedal commands. So that's another way. The hand wheels are moving the 2 wheels in the same direction, just so you know about that. And there's also the steering disconnect panel. So let's talk a little bit about that. That's installed on the nose landing gear. And so with this steering disconnect panel, we have, you know, different things we want to make sure that you understand about disconnecting properly, because, you know, we want to, if in case you have to tow the aircraft, you want to disconnect the steering. And you do this with a tow switch. The tow switch is there, and then you would have it in the off position. Okay, and doing that is going to allow that the steering to be in a free castering mode. We'll talk a little bit more about that later, but that's just enabling it to move, kind of move wherever and just be flexible, if you will. So you have that disconnect panel. All right, and what it's doing, you have the system that's set to the towing position with a pin. There's a pin there for that. There's actuators that are going to be put in a bypass mode when that is in that tow position. All of the signals are going to be sent to the CPIOMs. If you recall, that's your core processing input and output modules, where it's going to be de-energizing the isolation valve in the closed position. So that's going to prevent the operation of the steering of the wheel. All right. There's also a green light indication that shows you that the switch is in the towing position. Okay, that's right on the steering disconnect panel. Okay, and like I mentioned before, that there's the hand wheels, which are your primary steering inputs. There's a push button on the hand wheel units that when it's pushed, it's going to cause that control system to disregard the commands coming from the rudder pedal during any pre-flight checks. And also it's going to be preventing any nose wheel tire scrubbing. Okay, so that's just details on that. There's also an oversteering detection. You know, it's one thing that's important about angles when it comes to the wheels, you know, moving from left to right, is how far can it go? Because it can't go 90 degrees. You take, right, if you have the nose wheels pointing, you know, aircraft center in front, you know, when it takes a left or goes to the right, when it turns, there's a certain, you know, max number of degrees. So in here we're talking about the deflection that can go to its limit of plus or minus 77 degrees, okay, plus or minus either left and right direction when you're towing or pushing back the aircraft. So you don't want to go beyond those limits, because obviously you're going to cause damage if you do. So just be aware of that. There's an oversteering detection that's going to give a visual warning of that excess travel that may be going on. And what's, you know, what sensors or what components do we have in place for detecting the oversteering? What do we have? Okay, that's going to be the deformable brackets. That would be one. And also your proximity sensors. So those are the two parts two pieces. You got your sensors, and then you also deformable brackets that are going to give you an indication of oversteering happening. And when that happens, you're going to be getting, there's different warnings and indications. You've got the alerts that are going to show up on the warning display, and also, you know, there's going to be a generation of reports from the aircraft condition monitoring system, and then you have indications to the ground crew. Okay, so that would be all of you. Of course, you need to visually inspect the nose landing gear at that point. What's going to happen with those brackets are going to be just sheared off. That's the reason why they exist. And then that's the indication right there, okay, that it's too much. Okay, and you'll see that on the steering disconnect panel, there's a steering warning that'll be showing. That'll be in a amber colored light. Green means you have a disconnect. In other words, just what you want, and that's a good thing, because that's the whole idea of the disconnect panel. Okay. All right. One of the things to be aware of is, before you do any of this stuff, you want to make sure that the aircraft is in the park. Okay, as in the park is on, in the on position. All right. Okay, so we've gone on some of those. Let's talk a little bit more about the inputs and kind of follow a little bit on the sequence of things. So let's just start with to get more of a feel for what's happening with inputs and outputs and everything in between. So with the nose wheel steering, you have the inputs, like I was saying, you have that from the cockpit. Those are coming as electrical signals, and that's your kind of like your steer by wire, because they're electrical. And they're, like I said, your inputs are coming from rudder pedals or your autopilot or your hand wheels, and those signals are going to be picked up by the CPIOMs. And that's going to be the wheel steering control system application of those CPIOMs, and it's going to be calculating and monitoring those commands as well as any feedbacks. There are 4 CPIOMs and 4 CRDCs. Okay, it's your common remote data concentrators, and those are going to be operating redundant sides, you know, side 1 and side 2. Those CPIOMs are collecting all that data, and then it's going to be, you know, monitoring what's happening with that. And just keep in mind, with the pedals and the autopilot, those commands are actually going through the primary and secondary computers, okay, your prims and secs. Okay, and it's going to take that combination and convert it into an angle, because that's what the objective is. By the way, we'll just note that there are 2 actuators on the nose wheel steering system, so you can operate and move in that particular commanded angle. Alright, so we have the demand orders that are coming from the rudder pedals and autopilot that combined are giving that are converting all of that into a demand angle. And then you have the hand wheel demand orders, which have a decreased angle deflection authority in relation to the aircraft speed. There's a relationship between the angles, command or demand angles, and aircraft speeds. And the idea there is just to make sure that there's not too much angle going on between, or excuse me, there with left or right. Your hand wheel steering orders are only possible if the aircraft is confirmed that it's on the ground, so it's going to be getting data from your LG or leggers system, okay, your landing gear extension retraction system, and then your rudder pedals position and also the autopilot commands are going to be having a decreased angle deflection authority in relation to aircraft speed. So that's going to be at different degrees. And all of those are sent to an isolation valve. That's just to ensure that there's hydraulic supply available coming from the yellow system, or yellow hydraulic system. There's a hydraulic block and a servo valve that's going to be adjusting the flow of that hydraulic fluid. That's going to be going to the steering actuators. Okay, so just so you know, the little bit of a sequence that's going on with those inputs, the electrical signals, and then all that being converted into a demand angle. And then again, they're going using the CPIUMs. They're going to be calculating all of that and then giving that feedback. All that going into giving commands for the adjusted flow on the hydraulic fluid that's going to the actuators. The hydraulic block, you have different components. There's a return check valve there that connects the steering actuators to the return circuit on the high pressure system. Also, you have rotary variable differential transducers, your RVDTs. Those are responsible for measuring the nose wheel angle position. That might be a test question, so hint, hint, highlight that one. So that's what the RVDTs are doing. Okay. Your CRDCs, your common remote data concentrators, are supplying power current to the selector valve. Okay, that's your nose isolation valve, and the nose wheel steering servo valve. So they're getting inputs from the RVDTs. And there's simple diagrams, best to look at if you're interested, looking at actual schematics to give you a better idea. And of course, you're referencing your aircraft maintenance manual and all the different manuals that are involved there, especially with schematics. All right, let's kind of go a little into the logic. The logic is you have your nose landing gear, main landing gear compressed. You have at least one engine master lever in the on position. Remember, we talked about the yellow hydraulic system. This is what we're dealing with here. The main landing gear, if you recall, is drawing its supply from the green hydraulic system. And then another aspect to the logic and conditions is your towing lever is not in the towing position. All right, let's see. I think it's time for a question somewhere. All right, what is the function of the hydraulic block? Okay, just refer to your handout. This is question number 16 on your handout. Okay, on your video notes and review. What is the function of a hydraulic block? Is it to stop the isolation valve from opening, or is it B, adjust hydraulic flow? Okay, it's the second answer. Question 17, when does the nose wheel steering go into a castering mode? I know I mentioned castering. Just kind of it's flexible, it can move around. It's when the nose wheel steering or hydraulic systems fail. Okay, I haven't gone into it a little bit in detail, but that's what it means. And then when the rudder pedals are applied. Castering mode happens when systems fail. It could be the hydraulic system or the nose wheel steering system itself. If there's a failure there or both, that nose wheel steering will go into a castering mode. Okay. All right, so let's go back to our lesson. All right, and since we're I mentioned castering mode. It is just that. I mean, if you have a failure of hydraulics or just the system itself, then you're going to have this castering, okay, that's going on. It just means that the nose wheel can just move freely, okay, in the direction of the aircraft moving. There's a pressure that's kept by an accumulator and also a return check valve, okay, and that's just there to prevent cavitations in the actuator chambers, just keeping that equilibrium going, so it doesn't have prevents that cavitation. That hydraulic fluid can move also from one actuator to another. Remember I said there's two actuators. There's also an anti-shimmy damping function that's part of all of this. Okay, all right, now let's go into talking a little bit about the actuators, since I know I did mention about the actuators. Like I said, there's two. They're parallel to one another, and they're operating around a rotary collar, what's called a rotary collar. And what it's doing is it's giving the steering rotation. That's why you have the rotating collar. So this thing is, the actuators are attached between the upper and the lower flanges, and the rod ends are attached to the rotating collar. So it's transmitting that movement to it. The hydraulic connection enables a crossover when the actuator reaches a full retracted position. So that's the mechanism going on and all of that. There's a minimum torque that's coming from the actuator. Okay, so there's again certain degrees. It's just to make sure that you have a certain travel and it's not going past a certain number of degrees. In this case, we're talking about 72 degrees. Okay, all right. So I'm gonna make sure I didn't miss anything here on your, we talk about as far as questions. Okay, let's go into backup steering. We're going to talk about active differential braking. So be aware of it. Active differential braking is also referred to as backup steering. So, for example, if you have a failure of the nose wheel steering, okay, I know earlier we talked about failures. The blockage, there's going to be a blockage of let's say the blockage of the active runway on the landing is, it's going to be possible. So you have a backup steering mode that's used for this. And this automatic differential braking, okay, active automatic differential braking is just allowing the flight crew to, leave the runway with the hand wheels. Okay, so it's using the automatic or aircraft braking system to command a differential braking situation, so it can move the aircraft. And there's three different systems that are involved with this differential braking. You've got the braking control system. Okay, that's your actuation of your automatic active differential braking, and then you have a flight control and guidance system, and that's for your control, and then your wheel steering control system. Okay, so those are your three systems: your wheel steering control system, flight control and guidance systems, which is your FCGS, and then also your braking control system. Okay, and just so you know that these are hand wheel demand inputs in order to achieve this. And then, of course, the computer for the guidance system is receiving the demand, and then it's sending those commands to the braking control system. Okay, so, and then the last thing just to mention is the zeroing of things. Okay, zeroing just means you're aligning things, and in particular I'm talking about electrical and mechanical zeroing of your components. With the electrical zero, okay, I'm talking about the rotary variable differential transducer that would need an adjustment. So there's an adjusting that can go on here. And of course, before you do an electrical zero, okay, adjustment or alignment, you want to make sure that you do a mechanical zero. So that's why I mentioned them both together. You have to do a mechanical zero, making sure that the nose landing gear is physically aligned and centered within, of course, a certain range before you do your electrical zero of the rotary variable differential transducers. So just keep in mind, just follow the marks that are on the nose landing gear when it comes to zero positioning. Okay. All right, let's see. I want to make sure I cover some review questions for you if we have any left. Okay. All right. Looks like we covered everything here. Just again, there's if you have any questions or want to get more detail on certain aspects of the nose landing gear, the nose wheel steering, please email us and we can certainly answer to the best of our ability with that. All right. Well, this concludes our session 7 on nose wheel steering for the landing gear on the Airbus A350. Welcome to session 8 on tire pressure indicating system. The tire pressure indicating system is going to be measuring and monitoring the tire pressure, and this is to ensure that maintenance is making sure that the pressure is where it needs to be and not too low before takeoff. There are sensors that are located on the wheel rim, and those sensor holders are going to be changing the data into wireless signals. Those are going to be going, signals are going to be transmitted to the rotating interface unit, and from there will be digitized and sent over to the static interface unit, which is located on the wheel hub itself. So as far as different components, just to, making a listing, you gotta have pressure sensors, you have the rotating interface unit, okay, essentially the hub cap, and then you have the wireless signal that's going to be going from there to the static interface unit. So you have a rotating interface unit and a static interface unit. All right, and the control is coming, or all the data is going into the CPIOMs. Those are your core processing input-output modules that are going to identify and determine whether or not the tire pressure is where it needs to be. If it's too low, then the warnings are going to be sent to displays about that. Whether it's either one or more of the wheels are too low, or there's a difference in the pressure between the two. If it turns out to be a certain number, then it's a certain value, it's going to execute a warning for that. All right, so just being aware that that's what you have with the monitoring and of the tire pressure, and ensuring that the crew knows that there's low pressure, in which case maintenance needs to take care of making sure the tire pressure is up to where it needs to be. This concludes session 8 and concludes the entire GenFam for the landing gear on the Airbus A350. If you have any questions, please do not hesitate to email us with those questions, and we will do our best to get those answered to you as quickly as we can. Thank you for your participation.